Hello everyone, my name is Ignacio Cuauhtémoc Benítez Zúñiga, and for me it's a pleasure to present this video abstract entitled Inline Wideband RF MEMS Switch Integrate on PCB using PCB Planarization in collaboration with the professors Alexander Martiniuk, José Ismael Martínez López, and Jorge Rodríguez Cuevas, all of them researchers of the Engineering School of the National Autonomous University of Mexico. The growing demands in wireless and satellite communication systems had motivated many researchers to study RF MEMS technology. Some challenges in the area of telecommunication engineering demand systems that require every time low power consumption, read bandwidth, being monolithically integrated in RF and microwave circuits with low loss, high quality factors, high tunable characteristics, high linearity, and inexpensive. Some of the systems that is desired to have a higher performance in the super high frequency and extremely high frequency band with lower costs are the reconfigurable reflector arrays and active frequency selective surfaces. They have been studied for their capability to adjust their response to a varying dynamic scenario imposed by the new generation of wireless communication systems. The main advantage is the operational control of the radiation pattern and the ability of the fast electronic scanning. These arrays are commonly fabricated on microwave-friendly substrates. Therefore, the development of the low-cost RF switch that can be integrated to the PCB substrate during the fabrication stage is of primary importance to reduce manufacturing costs and time. Thus, it is highly desired to develop a relatively simple and expensive fabrication process for the RF MEMS switches. In this paper, we present the design, fabrication, and characterization of an inline wideband RF MEMS cantilever beam switch with metal-to-metal contact and electrostatic actuation integrated on a coplanar waveguide and fabricated with PCB technology on a flexible microwave-friendly substrate. The proposed switch accomplishes a planarization based on benzyl cyclobutene. The developed fabrication process is relatively simple, comparatively inexpensive, and it implies a wide use of benzocyclobutene as a planarization material, that to reduce the surface ruggedness of cantilever beam, enabling a high repeatability of the fabrication devices. The proposed radiofrequency MEMS switch with a metal-to-metal contact is shown in the screen. This switch is integrated to a coplanar waveguide embedded on a microwave-friendly substrate. When the switch is in the off state, the free end of this cantilever beam is suspended above the central conductor with the initial gap. Therefore, the continuity of the central conductor is interrupted, which prevents the transmission of the radiofrequency signal across the coplanar waveguide. The commutation to the on states occurs when a control voltage is applied between the cantilever beam and the actuation electrode. The electrostatic force applied to the cantilever beam causes a deflection of the free end over the central conductor. Thus, a metal-to-metal contact of a protruding feature that represents the contact area and the central conductor is achieved, enabling the continuity of the RF signal through the central conductor of the coplanar waveguide. Fabricated MEMS switch demonstrated an actuation voltage of 30 volts and commutation time of 425 microseconds. The fabricated switch demonstrated isolation better than 13.1 dB and insertion loss lower than 0.63 dB in the frequency range from DC up to 12 GHz. In frequency from 12 to 20 GHz, the insertion loss is lower than 1.16 dB and the isolation is higher than 9.6 dB. Finally, in conclusions, The developed MEMS switch used benzocyclobutyne as planarization material with a low complex fabrication process. The switch was monolithically integrated to a coplanar waveguide printed on a standard Rogers substrate using PCB techniques. The presented switch has a good radio frequency and electromechanical behaviors in a wide frequency band. Thus, the switch based on the developed process can be used to the fabrication of multi-phase shifters, reconfigurable reflector arrays, and active frequency selective surfaces, where a considerable number of switches is required.